Unfortunately, I could not be in Indonesia with you today. However, I had the pleasure of being in Indonesia, in Jakarta specifically, in late November, and great to see the progress that Indonesia is making as a country. It is really phenomenal, the advancement that is occurring within Indonesia at the moment. So today I'm going to talk a little bit about the neutron scattering applications at ANSTO, and particularly in material science, and give a bit of an overview of the facility. So let's go forward. There we go. So my outline of my talk, I talk a little bit about ANSTO, what is ANSTO and what is in our OPA reactor, why we use neutrons, talk a little bit about the Australian Centre for Neutron Scattering, our user program, science, and our industry program. So I'm going to give a bit of a flavour of what we do. So for those that don't know ANSTO, so ANSTO stands for the Australia's Nuclear Science and Technology Organisation. We are a leader in nuclear science and technology in Australia and in the world. We've been operating safely for over 60 years. At present, we have about 1,350 employees located across 2 campuses. So we have a campus in Sydney at our Lucas Heights and in Melbourne at the Clayton campus. And at present, we have about over $1.5 billion worth of research infrastructure. And we manage that on behalf of Australia and primarily for use for Australian researchers to undertake science for both industry and research problems. And as you can see down below here, this is actually a photo of the ANSTO Lucas Heights campus, which is in south of Sydney, surrounded by beautiful bushland. And of course, being surrounded by bushland, we also have challenges with bushfires as well. So we've had a few occasions in the last couple of years where we've actually had fire come up to the fence of our campus. So in terms of national research infrastructure, ANSTO is home to most of Australia's national research infrastructure. So we have and there's been some significant investments in research infrastructure. We have the Opal multi-purpose research reactor here. You can see that one. We have the Australian Centre for Neutron Scattering, which I lead, which uses neutrons from the Opal reactor. ANSTO Centre for Exoto Science, where we're actually undertaking a lot of work in terms of carbon dating and isotope analysis, as well as now doing a lot of ion implantation into materials. And of course, we have the Australian Synchrotron in Melbourne, which is Australia's largest, brightest light source in our facilities. So just a bit of background about the Lucas Heights campus and OPA reactor. So this, as I said, we're surrounded by beautiful bushland. You can see Sydney back over here in a very far distance. So we're actually about 30 kilometres from the CBD. And ANSTO has quite a rich history in nuclear reactors. In fact, we've actually had 3 reactors on our site. We had first of all a high-fire reactor, which was a 10 megawatt Dido reactor, which shut down in 2007. We had a Mawata 100 kilowatt Argonaut reactor, which was shut down in 1995, but has been fully decommissioned in 2010. If you go to that site at the moment, you would not even know that there was a nuclear reactor there in the past. And of course, we have the jewel in the crown. We have our OPA reactor, which is more recent, which was commissioned started in 2006. As I mentioned, we're located a little bit of a distance from the Australian Synchrotron. At one point in time, we were going to have the Australian Synchrotron located here at ANSTO at Lucas Heights campus, but they've decided to build that down in Melbourne. So you can see we have quite a good location and a large amount of research infrastructure on our site. Just to talk a little about research reactors around the world or neutron user facilities, there is a number of facilities in the world, and we typically break it up into 3 regions. We've got the Americas, we've got Europe, and we have Asia Oceania. And the neutron scattering associations across the world are split into those 3 regions, and we have a number of meetings that occur both within each region, and we have the International Conference in Neutron Scattering every 4 years. Over the last few years, we've had a number of reactors shut down, permanently shut down. So we've had, in the US, we've had Lance facilities not shut down, but actually moved to be not a user facility, the NIU in Canada. We've had Saclay reactor in France. We've had Helmholtz in Berlin in Germany, shut their reactor down as well. So there's actually been a decline in the number of facilities around the world. We've also had some challenges with some of the reactors in the world, and at present, the NIST Centre for Neutron Research is currently shut down, with hoping to restart. It's been down for 2 years now, hoping to restart either late this year or early next year. We've got the FRM2 reactor in Munich is currently shut down as well. So we've had some challenges in terms of the number of facilities around the world, and there's been what we call a drought of neutrons. And we've also been seeing an impact of that. So this is a layout of the Opal facility on the Lucas Heights campus. So we have the reactor in the middle here, and you can see what we call as the chip basket, which is a protective structure, which is in the event it's supposed to stop the penetration of a Boeing 747 from penetrating the reactor, and what we call the plane shredder. We have a neutron guide hall out here where we actually have a large number of our instruments. We have some offices located around the place, and we have our visitor center, and it's right next to the existing high-fire reactor, which is currently in a state of shutdown and presently being decommissioned. You can see on the other side of the reactor here, we actually have a large space that's been reserved for a second guide hall. So we actually have capability to expand our facility further with the expansion of a second guide hall and further instruments. So this is a photo of the Opal reactor when it's operating. So you can see the beautiful Cherenkov blue radiation there, which is from beta particles moving through water for the radioactive reactions that we have within the facility. It is a 20 megawatt reactor. It's an open pool. And because of it's been open pool, we're able to do a lot of our operations underwater, which is quite good and have a high availability. We use plate type fuel, low enriched uranium, trying to avoid the issues around proliferation. We've been operating since 2006, and we have a very long design life. So we've presently got a lifetime out to 2045, and we expect with some further extensions out to 2055. So looking at the reactor here, you have what we call the core in the middle, which has 16 fuel elements. We have, this is the main cooling pipe, which brings cooling water into the reactor. We have what we call the reflector vessel, which is this structure around the outside. Within the reflector vessel, we have heavy water, and within that vessel, neutron fluxes build up within that region. And within that, we then actually have penetrations down inside the vessel, which allow us to do irradiation. So we have locations here for silicon, which are for the transmutation of silicon. So we currently provide about 60% of the world's high quality silicon for high-end applications such as aerospace, fast trains as the sort. You can see here we have a number of radiation points, and this is for making molybdenum-99, which is the primary component which is used for doing diagnostics within medical, so radiopharmaceutical. At present, we provide the story is 1 in 2 Australians will receive some radiopharmaceutical that's come out of the Opal reactor in their lifetime. So we have quite a high impact there. You can also see on the side here, there's actually a number of pneumatic tubes. We're able also to allow targets to be irradiated in the facility and then removed as well. This is a photo of the fuel element, which has 21 plates. So there's 6 of these within the core. They're actually it's uranium silicide coated with fuel cladding of aluminium on the outside, so to prevent leakage, and water is forced up between these plates to keep the plates cool. This is the operational days or the availability of the reactor over the since 2006. We achieved our target of operation of 300 days in 2015, and you can see that we've consistently achieved very high utilization availability rates. We had a long shutdown in 2021. You can see the number of days dropped down. We're on target to achieve our 300 days this year and also next year. And then in 2024, we're going to do some major maintenance and replacing a major component. But you can see it's a very high availability reactor, which is great for both making radiopharmaceuticals, but really good for neutron scattering. So we have lots of neutrons. So I just want to talk a little bit about why do we actually use neutrons. So neutrons actually have a wavelength, so a de Broglie wavelength, which allows us to probe the structure and dynamics of materials. And we can look at length scales all the way from a human hair all the way down to silicon atoms. So we can either be doing diffraction, crystalline materials, we can be doing small angle, which is maybe looking at DNA and influenza virus, and then all the way up to basically USANs and all the way up to imaging. So we can cover that whole distance in terms of what we can actually study in terms of structures. The one big difference that is between neutrons and X-rays, so people always ask, well, why don't you just don't go do X-ray diffraction or small angle X-ray scattering or an X-ray technique? Well, neutrons actually have some very different properties with atoms when they interact with them. So the scattering of X-rays is primarily with the electrons and the electron crowd around an atom, and so it linearly increases with atomic number. However, for the scattering properties which are here for neutrons, it actually varies randomly across the periodic table. And so, for example, if you had a compound that had manganese and iron in it, using X-rays, it's very difficult to differentiate which atom it is. Within neutrons, you can see here, you have manganese and iron have completely different scattering lengths and allows us to clearly differentiate when we go and do our modeling. The other one is actually, the scattering properties also are different between isotopes. And the big one that we take advantage of is hydrogen and its isotope deuterium. So you can see here that they have completely different scattering. So what we are able to do is we can actually go and replace hydrogen with deuterium, maintain the same chemical properties, but change the scattering properties significantly. And this is what is quite heavily used within neutron scattering. And this is the example here. So for hydrogen and deuterium, the neutron scattering length is minus 0.374 for neutrons, and for deuterium, 0.667. However, for X-rays, it remains the same, okay? So what we're able now to do is we have two ways that we can actually introduce contrast into our samples. We can do external contrast variation, where we potentially could have mixtures of light water and heavy water. And what we can do, and you can see this here in this graph, if we have mixtures and we had a certain mixture, we can actually match the contrast of a particular component within your sample. And so, for example, making it disappear. Under this scenario, you in theory should have no scattering at all. But also we can do is we can actually have different mixtures and essentially get a set of data patterns which a model must fit. The second way of actually introducing contrast is actually we can go and synthesize molecules and replace the hydrogens in them with deuterium. And we can typically do this for biodeutration, but also for chemical deuteration. And at ANSTO, we have a facility called the National Deuteration Facility, which sole purpose is providing, well, it's not so, basically deuterated components or deuterated materials. Initially set up for neutron scattering. So here's an example here of a surfactant molecule. They can go and deuterate the tails and the heads, or you could, in theory, could just go deuterate the tail and not the head, and allows you to, for example, if you're looking at drugs within, and where is the location of a drug within a liposome or within a liquid crystalline material, you could go and identify where the drug is by simply introducing deuteration and doing neutron scattering measurements. However, the neutron deuteration facilities, it's actually done a lot more work in terms of just moving away from neutron scattering. More recently, they do a lot of work now in proteins and trying to work out the structure of proteins so they can deuterate the proteins. Similarly, mass spectrometry to try and understand what the reaction mechanisms within molecules are. And this most recent one is actually now looking at the kinetic effect. So the bond between carbon and hydrogen is much less than the bond strength between carbon and deuterium. And that enables it to be then used within systems where, for example, where you can have within the body, with drugs, for example, where the body would actually target these bonds and would break them down. This bond is stronger, so therefore, if you have for example, a pharmaceutical within the body, it may have a longer lifetime and therefore have a much better effect upon the body and less side effects. So you can give a lower dose, but also it then remains in the system and the less prone to attack from the body. So we've been doing a lot of work in this area now, and obviously there's pharmaceuticals, there's also looking in healthcare, and also beauty products as well. So there's a lot of opportunity in that space. The other reason why we use neutrons, because neutrons actually have an energy which is very comparable to atomic and molecular motions and dynamics. We have a number of techniques where we know the energy of a neutron going in, and through interactions with such materials such as this, for example, in this interaction with this molecule, it may gain or lose some energy. So we can now start to look at the dynamics of those materials. And we can look at everything here from a breathing mode and this compound. You can look at the flexibility of a protein, or even looking at flexibilities of polymers. And we have a number of techniques within our facility which covers both length scale and energy or time motion as you can probe. So we do both structure and we're able to do both dynamics as well. Because the interaction of a neutron is primarily with the nucleus, the analogy is a nucleus is the size of a pea on a football field. So the probability of interacting of neutrons with that nucleus within an atom is really quite low. So therefore, we have quite a high transmission, and it can also get high and penetrate deeply within our equipment. So this is a good example here where we had a sample, a very large piece of pipe, where we're able to get the neutrons in and the neutrons out and study the welds or the residual stresses within that material. Similarly, we can also get into large pieces of sample environment. So neutrons actually have a spin And what we have from the reactor, if you do the simple analogy, is we have half the neutrons coming from the reactor have a spin pointing north, half pointing south. We're able to remove all the ones, for example, pointing south and just have pointing north through polarization methods. And when a neutron interacts with a magnetic sample, it can actually change its spin. So dynamically, we can actually look at both the structure and also the magnetic properties of materials. So this is quite important, as neutrons are the killer app for magnetic materials. And so we can get, for example, and here, this is our large 12 Tesla magnet. We can get the neutron beam in and neutron beam out, and also study a magnetic material inside a large magnetic field. So this is the layout of the Australian Centre for Neutron Scattering. We presently have 15 neutron beam instruments, which are available to the research community and industry. We have 5 diffractometers, 3 small angle scattering spectrometers, 4 inelastic spectrometers, 2 reflectometers, and 1 radiography tomography instrument. We have a partnership with Taiwan. National Science Council of Taiwan have constructed a neutron beam instrument at the Opal reactor, and this instrument is available for Australian researchers. We also have a partnership with Helmholtz-Zentrum Berlin. As part of its reactor being shut down in 2016, they donated one of their instruments to us, the BioRef reflectometer, which we have now named to be the SPATS reflectometer. So we have quite a large amount of partnerships. We also have some other equipment as well. So I talked about polarizing the neutrons. We've got a helium-3 polarization station. We've got a SAXS instrument, a reflectometer, ppm magnetometer, ellipsometer, and a quartz microbalance. So we've got ancillary techniques to go with also the other experiments you do on neutron scattering instruments. So just to give you what it really looks like in the guide hall, so this is actually looking back towards the reactor. The reactor's back up here. This is all of our instruments located right, from the reactor, and you can see that it's quite a busy environment, quite packed in terms of components. We have a nice viewing platform up here where we have about 15,000 school students come through every year and have a look at the science we're doing in the guide hall. We have some capability to expand here, so we're actually going to be putting a couple of instruments and beam lines down through there at some point in the future. So just talk about what we do and what we are. So we have a number of strategic objectives which we talk about ourselves. We actually have about 78 people working for us, with 5 from the National Science Council of Taiwan. We have a large number of students and postdocs. We have 15 instruments. We're typically giving about 188 publications per year. Of the 300 days that the reactor runs every year, we give 225 out to both researchers and industrial clients. We typically run about 450 experiments per year, and we typically have about 1,400 user visits. So we have lots of people coming and doing experiments at ANSTO. Our target utilization is 85% and availability is 95%, and we achieve that quite regularly. We have some external funding, which within Australia, which is great to try and supplement what we're doing. We get strategic partners. The other thing that we do is we also partner with the Australian research community on grant applications to the Australian Research Council. So we're presently on 10 research projects, and the ACNS staff play a very important role, not just as instrument scientists to run the experiments, but actually as thought leaders and innovators within the research projects as well. We have an industry program, and I'll talk a bit more about that, where we actually have research companies that pay access to use our facilities. And we also have a large number of grants as well. We partner with industry too. So talking about utilisation, so this is just our utilisation over the last 2 financial years. So financial year in Australia is from July through to June. So you can see here, this is in the period of quite a large amount of COVID impact. And then we've got a target availability of about 85%. And you can see that our utilisation is doing all right. If we took out the impact of COVID, we would have reached our target of 85%. And this year, we're more than likely will reach our target of 85%. So we're utilising the facility quite well.
You have 3 minutes left. Could
3 minutes.
you wrap your presentation?
Okay. 3 minutes. Okay. All right, I'll need to wrap up. So we have a number of ways to access our facility. We have merit, user pays, and discretionary. I'll just jump through this. So we have quite a high demand. We're typically oversubscribed of a factor of 2 or a factor of 1.5. You can see here we have quite a large demand around the world, including Indonesia in the present round. Notification just gone out today, demand in Australia. Science, talk a little bit about that. So we have quite a good level of publications. We are able to do some some really good science in terms of the instruments. Here's just a couple of examples in material science. So this is an example where we have a surfactant which actually can change its structure when irradiated by UV light, going from long red rod-like micelles to spherical micelles. And using a quartz cuvette cell, we're able to see that alignment of those if you put that within a shear field. Here's a good example where a hexagonal planar transition metal complex was predicted to exist by a Nobel Prize winner about 100 years ago. This was only discovered in 2019. And in this case, we were able to locate the location of the hydrogens in here. You cannot see the hydrogen with X-rays. This is a good example here of looking at how increasing the molecular weight of a polymer, it actually has a linear relationship. And here's another very good example on Sequin Pelican, where we've had ferrochlorific crystals, where these crystals, when compressed, give out energy. When they allowed to expand in, they suck in energy, so they can act as a little micro fridge. And these were undertaken with a number of measurements from within Australia and also within Japan. We have an industry program working across a number of the key areas within Australia. Within that, we can have industry working with us with merit or commercial access or collaboration, and we have different value for those arrangements. Large number of clients ranging everywhere, and you can see that there's quite a lot there in advanced manufacturing, and big companies like Ford, Honda utilize our facilities quite well. A couple of quick examples in terms of materials. So we do a lot of work in battery materials, so understanding the structure and function of batteries. So this is, for example, lithium ion. We've done quite a lot of work in this, and we actually pioneered the in situ measurements of doing neutron scattering. And I believe Niraj talked a little bit about much of that earlier today. So this is led by a researcher called Vanessa Peterson, who leads the energy materials. So she does a lot of work in understanding battery materials. And this is a typical experiment we would undertake, where we would have a neutron beam, we'd have a battery in the beam, we've got a battery controller, so we can actually charge and discharge this battery, international collaborator detector, where we capture the neutrons. And we can do this in operando, so we can actually do the neutron scattering measurements whilst you're doing the charging and discharging process. And the outcome from this is here, for example, was we go through a process of charging and discharging for a battery. It actually changes its crystal structure as it goes through the peaks of charging down to discharge.
Schulz,
Yes.
Dr. Schulz, I think time is up. I think we can continue our question and answer.
Okay. All right. Any questions?
Hey, you have any question? So I invite the question from the floor. Prof. Effie, you have any question?
Okay, thank you. Thank you for excellent talk. Jamie?
Yes.
Can you hear me?
Yes, I can hear you.
Yes, nice. Nice to see you again, even only by online. Okay, so we have some students here. They're coming from several, university from Indonesia. So what do you have a program for the students? I mean, to perform the neutron experiment in ANSTO?
Yeah. So for us to do experiments at ANSTO, anybody can apply for beam time. So the proposals are received, and based upon we assess them based upon merit. And so if the students' research that they've put in that proposal, they're able to come and do the experiment if it's approved. Let's bring that back. So under this program here, where it comes.
Okay, so they should make a proposal. Yes, that is competition.
Yeah. So we have run a user rounds 2 per year. So with beam time days closing, the deadlines on the 15th of March and 15th of September.
Okay. Thank you.
The one thing we do have is, and most of the experiments, the expectation is you come and do the experiment. For powder diffraction, we have a mail-in round, so you can actually mail the sample to us and we'll measure it for you. And that details of that are on our website.
Okay, so this is possible for us to send, and then but should we start also with the collaboration with the well, instrument scientists there.
Yeah, so we on our website we have all of our instruments and also the instrument scientists that are associated with those instruments, and they're readily accessible and contactable by simply emailing them and asking about the instrument or what can be measured or what cannot be measured. We run also neutron schools regularly throughout the year, so there is always the opportunity to participate in a neutron school. A lot of those are run in hybrid mode now, so there's an opportunity for researchers in Indonesia also to participate in those neutron schools.
Oh, thank you. Thank you. We'll give this announcement to our students here. Okay, thank you, Jamie. I give back to the moderator.
Okay, thank you, Prof. Evi. You have any questions regarding to the neutron scattering? Time is up. Okay, just one question.
Can you hear my voice?
Yes, I can hear your question.
Okay, thank you for the what's that? I'm sorry, it's a little bit nervous here. I'm very interested that you say that there is opportunity for students, actually college students, to participate in your program. My question is that, is there any limitation for the students who want to collaborate or want to send the proposal to your company or something else? And it's like, the limitation is like, it's not to be final student, or it's possible for sophomore students to submit a proposal and collaborate with your program. Thank you.
Yeah. So we don't have the restriction. So there is no restriction in who can submit a proposal. The intent is that researchers come and undertake their experiments at ANSTO. So there is the challenge around getting travel funding. So that would be something you'd have to try and work within Indonesia. But as I mentioned before, for the mail-in round for Echidna, there is no need to travel, and you can simply just mail your sample for a powder diffraction measurement.